morning, everyone. We'll get started today. So in chapters 7, 8, 9, we're united on the topics of or 6, 7, 8, 9 on the topics of the electron to the nucleus of the atom to Lewis structures and then into shapes of molecules. Now chapters 10 to 12 are another unit. So chapters 10, 11, and 12 are on the topics of gases in chapter 10, liquids in chapter 11, and if you can guess, chapter 12 is on solids. The good news for chapter 12 is we're only going to cover like maybe a section of chapter 12. So we're just going to talk about a few details out of chapter 12 towards the end of the class. And so we're going to focus primarily on chapters 10 and 11. And then once you get into Chem 1220, the first chapter is on solutions. So you kind of go gases, liquids, solids, and then into solutions to start Chem 1220. Okay, so let's get started here on chapter 10 on gases. And so we'll talk about gases and pressure, the ideal gas law. Some of you guys might remember the ideal gas law. I always like to start with things we might remember, because if you remember this equation, then you'll certainly be able to appreciate it, that we use it here in chapter 10. This equation describes an ideal gas. So an ideal gas is a gas that obeys this equation. This relates the moles of a gas to the temperature of the gas. But the temperature specifically in Kelvin or in an absolute scale. An absolute scale would mean that the lowest temperature would be 0, where temperature is impossible to go negative. So we have to use some sort of absolute scale, such as the Kelvin scale here. One of the things for chapter 10 that we'll have to use is anytime we're plugging into an equation, we have to be in Kelvin. Technically, you could also be in whatever the Fahrenheit version of Kelvin is. Anybody know that scale? I think it's called Rankine. Technically that would work too, but rarely do we use that in this class. V is of course the volume of the gas, and P is the pressure. So we'll talk a little bit about pressure today, what it means, what it corresponds to, some different conversions between units of pressure. And in the last unit here, we'll actually show a derivation of the constant R. This is the ideal gas constant. And so we'll talk about what that constant is numerically, how we find it, and then talk about some problems that relate to this equation that we can solve. And so we'll talk about applications of the ideal gas law. We'll get into gas mixtures, talk about partial pressures, everybody's favorite topic called Dalton's law of partial pressures. If you haven't heard that one, we'll talk about that in the middle of the chapter. We'll try to describe gases and how they behave the way they do. We'll talk about that section called the kinetic molecular theory of gases. This will describe gases as non-interacting particles. So if we have a gas mixture, if you imagine having air, nitrogen, oxygen, that the particles just in the sample of air can bounce around, but they don't interact with each other. The particles aren't reacting together when they collide. So molecules can collide with each other, they can collide with the container. The collisions with the container are sort of where you get the concept of pressure from. So the more collisions with the container, the higher the pressure you would imagine for your gas sample. And then we'll talk about effusion, diffusion. So effusion is the escape of a gas from a pinhole. You can think about, maybe a pressurized tire has a pinhole in it. The air would be effusing from that pinhole. And then you can think about the diffusion of a gas through a medium. So this is the spread of a gas. Probably the most, one of the better maybe examples of diffusion would be the smell of like coffee, permeating through like a house, making its way up to the second floor. And so that's the spread of the compounds in coffee, making it and spreading through air. And so that's the concept of diffusion. So we'll talk about factors that relate to the rates of effusion and diffusion as we proceed into the chapter. And then we'll wrap up with a discussion of what it means to be a real gas. A real gas is one that doesn't obey the ideal gas law. And then we'll see that gases start to disobey the ideal gas law when the particles start to stick together. And so particles begin to stick together when they're starting to condense. So condensation will allow particles to stick together and eventually form the liquid state. So the ultimate formation of liquids is the complete breakdown of the ideal gas law. If you think about it, it's where the particles don't bounce off each other, but they stick together. And then this will happen when we start approaching the boiling point, this is when the temperature drops. So at low temperature, we'll see that's where we're primarily breaking down our ideal gas law. But that's also where we start to head to the liquid state, and then that sends us into chapter 11 after that section. So let's talk about some characteristics of gases. So the physical properties of gases are quite similar. I'm sure you all remember a gas is a substance that expands to fill its container, and so that's a property that all gases have, regardless of the nature of the gas. Substances that are gaseous at room temperature are primarily comprised of nonmetallic elements, and so we're going to see nonmetallic elements with low molar masses are substances that tend to be gases at room temperature. So we can think of things like O2, N2, CO2, etc. So relatively small molecules. We also have the noble gases that, of course, are gases at room temperature. And so we can think of lots of examples of gases, and these are comprised of our nonmetallic elements. And so unlike liquids and solids, gases expand to fill their containers. You can compress a gas. So if you have a gas like in a cylinder with a piston, you can push down the piston and pressurize the gas. If you let go of the piston, it'll go back up. So gases can be pressurized, be depressurized through pistons, if you will, so they're compressible. They have low densities. The density of a gas is, of course, lower than the liquid or solid phase. If you think of a solid, particles stuck together, liquid moving around, gaseous state, they've separated. So liquid to separate into the gas phase, of course, the gas phase is going to have a lot lower density compared to the liquid phase. And then if two or more gases mix together, they're always going to form a homogeneous mixture, like an equally mixed mixture. We're not going to get a heterogeneous mixture within a gas mixture. If you think about two particles in a container, that you imagine particle A, particle B, you have different particles here, they have to be interdispersed. They're going to interdisperse. If you had all the B's collected at the bottom, all the A's at the top, that would be kind of strange because these particles are always moving. So the particles are always moving, they have to be always mixing, so we should always get a random mixture. And not like an ordered heterogeneous mixture. And so the properties that define the gas sample would be the temperature. We mentioned before, like let's use an absolute scale. Our temperature in Kelvin is our temperature in degrees C plus 273.15. Just really simple, making sure we remember that 25 degrees C. We add 273.15 to that, so that would be 298 Kelvin. So room temperature, 298 Kelvin. So temperature, pressure, we'll use a variety of units of pressure. One of the common units, we'll derive some of these in a minute, are like atmospheres, ATM. We'll use units like millimeters of mercury. We'll discuss in a minute too why we might use such a unit or how mercury applies here. We'll see that it comes from the use of mercury in a barometer to measure pressure. We'll use things like torr as well. There's other pressure units, but just a couple examples of pressure units. And we'll define their conversion factors as we go. Volume, primarily units liters or milliliters, but probably liters the most common unit here that we use for describing the volume of a gas. And then the amount of gas is often expressed as moles. So we'll calculate the number of moles. So if you have, for example, 2.016 grams of hydrogen, we might just recall that it's 2.016 grams per mole of H2, so that would correspond to 1 mole of H2. So we'll commonly use the moles of a gas sample. And if you recall from our ideal gas law, it's the amount in moles are what relate to the pressure, volume, and temperature, not the mass. And so the number of particles present in the container, if you think about a mole being an Avogadro's number, this would be 6.022 times 10 to the 23 H2 molecules. So it's this number of particles that define the gas sample. So it's really, if you imagine having a mole of H2, that it's going to behave, it's going to have the same pressure, the same temperature. If you imagine a mole of H2 at the same temperature and the same volume as, say, a mole of helium, they're going to have the same pressure. So it's all about the number of particles. So 1.0000 moles of helium at the same temperature and volume of the mole of H2 would have the same pressure. So it's all about the number of particles. It's all about having the same number of particles, then you get the same set of properties for your gas sample. And we'll see maybe why that is as we go to. So let's look at pressure. So pressure is defined as the amount of force that's applied to an area. So it's a force over a square area. If we start thinking about what atmospheric pressure is due to, well, it's due to the weight of the atmosphere that's accelerated by gravity. If you think of force, remember force from physics is mass times acceleration. So if you think of the mass times acceleration, where acceleration of the atmosphere is due to gravity, then you can realize that it's the atmospheric mass times gravity. So that's the force exerted by the atmosphere onto the surface area of Earth. I used to do this problem. It's really not all, it's like a fun problem to do, but then you get worried that you might see something like it again. But if you think of quantifying the actual mass of the atmosphere, this is something you can actually look up that scientists have somehow determined. You can take the mass of the atmosphere, you can take gravity, that's the force that's being applied onto the surface area of Earth. You can also look that up, and that you get that this pressure that's exerted by that atmospheric mass times gravity over the surface area is equal to about 100,000 kilograms meters per second squared. And so that this unit here takes on the unit called the Pascal. The units are actually meter to the, let me rewrite the units real quick. And the units, you'll probably never even use these, but I just want to make sure that I'm being correct here. So the atmospheric mass would have units of kilograms, gravity, meters per second squared, surface area of Earth in units of meters squared. And so then that gives us units kilogram, meter to the -1, second to the -2. And that unit here is equal to the SI unit of pressure that we call the Pascal. So 1 Pascal, and these pressure units are also re-given on the next slide. 1 Pascal is equal to specifically 101,325. Okay, I'm defining two different conversion factors. The Pascal is the kilogram, meter to the -1, second to the -2. So it's just equal. So 1 Pascal is 1 kilogram, meter to the -1, second to the -2. And then that pressure for atmospheric pressure, the standard atmospheric pressure is about 100,000 of that unit, so about 100,000 Pascal. So standard atmospheric pressure in the unit of Pascal, that's the SI unit of pressure. Remember how SI units are often defined off the base SI units like kilograms, meters, and seconds. So the SI unit of pressure, of Pascal, it's actually a unit we rarely use for pressure in a class like this. So we like to know what it is, and it's interesting that you can actually quantify and relate the quantity for the standard atmospheric pressure due to the atmospheric mass. It's also then, you could say, the mass of air that would be sitting above 1 square meter. So if you took a 1 square meter column of air straight up into the atmosphere, that it would turn out that there's about 10,000 pounds of pressure above every square meter. So it may be hard to imagine that above a square meter, all the way up into the atmosphere, that there's 10,000 kilograms of mass that's being accelerated down at a rate of about 9.8 meters per second squared for gravity, is where you get that approximate 100,000 value for the pressure in that unit of kilograms, meter to the -1, second to the -2, or what we call 100,000 Pascal. Now let's on the next slide look at some different versions. So 1 ATM, this is what we kind of think of as being standard atmospheric pressure. So 1 ATM being like the standard atmospheric pressure on the surface of Earth. This is equal to about 760 millimeters of mercury. Where mercury comes into play is you can use or construct a barometer where you take a tube that you fill with mercury, and then you have a vacuum inside of the tube. So you fill your tube with mercury, and then you like invert it in a mercury dish, and then the mercury settles, so there's a vacuum inside of our tube, and then the height of the mercury here has to counterbalance itself with the force that's pressing downward on that dish of mercury. So there's atmospheric pressure pressing down on our dish of mercury, and then the height of mercury is just counterbalancing the right mass to be in this column that's pressing downward on that dish of mercury. So we're just counterbalancing the mass of the atmosphere, the atmospheric pressure, with the mass of mercury in our barometer. And so it's this height here that you can measure. And there's, you maybe have seen a barometer before if you've ever seen one. It's a pretty long column because you have to have, at least, 760 millimeters to measure standard atmospheric pressure if it's 760 millimeters of mercury. So you'd measure the height of mercury. If pressure were lower, the height would drop. If the atmospheric pressure were higher, the height would raise in the column. So you're measuring the difference between mercury at the base of the dish to mercury at the top of the column. And this height corresponds to the standard, or to the measurement of the atmospheric pressure at the time you take the reading. So this is a way of measuring atmospheric pressure. We don't talk too much about barometers. You might see an example or two in the homework just to get a sense of how they're used. But it's just a way of also trying to understand why we use the unit millimeter mercury. So where millimeters of mercury come into play is that would be the height for what we call standard atmospheric pressure. And then the unit torr is just a synonymous unit that you also see used, where 1 torr is 1 millimeter of mercury. And so standard atmospheric pressure is exactly 760 torr. And so 1 ATM, just to make sure that we're clear here, is 760 millimeters of mercury exactly. So that's an exact conversion. And then standard atmospheric pressure, and that unit of Pascal, is the 101,325. So 1 ATM, standard atmospheric pressure, is 101,325 Pascal. That's also an exact value. That's not rounded. And so this would also equal 101. So 1 ATM would also equal 101,325 kilogram meter to the -1 second to the -2, if we're just thinking of that unit back to SI units. The unit bar, I don't think I've ever used this in a problem before, but you may have seen this unit in meteorology. You often see it for hurricane reporting for the pressure inside of the center of the hurricane, for example. But bar is a conversion to ATM. It's almost 1 ATM, but if you notice, it's the same value for the Pascal conversion. So 1 ATM is 1.01325 bar. And then another unit that we don't use a lot, but it's commonly used in other areas, such as filling car tires, such as actually filling a gas cylinder is often noted in PSI. But PSI stands for pounds per square inch. If you go back to the idea of pressure is the force applied to a square area, you can kind of see where pounds as your force per square area is where the PSI unit's coming from. But 1 ATM is equal to 14.696 pounds per square inch. So PSI, pounds per square inch. So pound per square inch. And so one atmosphere is about 15 PSI. So when you fill your car tire to 30 PSI, which would be probably pretty low for tire pressure, I think they're usually filled to 35 or 40 PSI, but that tire would have, if it has 30 PSI in it, would have about 2 atmospheres of air, and that's above atmospheric pressure. So it would actually have 3 ATM of air in it. So whenever you use a tire gauge to measure your tire pressure, that's the pressure above atmospheric pressure. So if you have ever had a flat tire and you put your tire gauge on it, it doesn't read at all. That just means it's 0, meaning it's 0 pounds above atmospheric pressure. So even a flat tire still has atmospheric pressure and it doesn't create a vacuum inside of it. Okay, so that's the PSI unit. So this slide here has a couple conversions. So we're going to convert 745.0 torr to millimeters of mercury. Now, if you recall, the millimeter of mercury was synonymous with torr, so this would be 745.0 millimeters of mercury, because torr and millimeters of mercury are equal to each other. If you were saying, okay, that on the previous slide, maybe it was a little confusing on how that worked out, we could always write this out just to make sure we're seeing this. We'd have 745.0 torr, and we might use the conversion that we have 760 torr per ATM, and then 1 ATM is also 760 millimeters of mercury. So of course we're dividing and multiplying by 760, so that equals 745.0 millimeters of mercury. If we want to convert to ATM, well, 760 torr or in 1 ATM. This is probably the pressure conversion we do the most in this class, is torr or millimeters of mercury to ATM or vice versa. So we do this conversion a fair bit, so just remember that there's 760 torr and 1 to ATM. I'm pretty sure we give you this conversion factor if you forget it, but it's one that we're going to use a bunch, so I think we're going to come to know it pretty quickly. So this should be a fraction of an ATM. It's 0.980. The conversion to Pascal. So we'd have the number of Pascal would be 745.0 torr. Now, there's a few ways we can think of this conversion. Like we can go 760 torr to ATM, and then ATM to Pascal. Or we can say 760 torr is 1 ATM. 1 ATM is also 101.325 Pascal, because both of those two units are equal to the same value of an ATM. So we could also have just written this out in 2 steps if we needed to. So if we need to write this out as 1 ATM here, and then 1 atmosphere is 101.325 Pascal in the second step. So it's 99,300. Well, I guess I should give one more sig fig. 99,330. Can't write at all. And technically, I should have given one more with the ATM. If we're thinking sig fig rules here, first time we've done calculations in a while. I was thinking today that on midterm 3, I don't think we needed a calculator at all for any of the problems. So we get back to doing some calculations here in chapter 10. So this should have been a 3 here if you're tracking sig figs. I feel like there's some boss of chemistry that would yell at me if I don't do the sig figs correctly. You guys are like, yeah, isn't that your TA? Okay, so PSI. So we just might have to have the value for the previous slide, but it's 745.0 torr. So 760 torr is 1 ATM. And it was 14.696 PSI. So that's 14.41. Does anybody remember the Deflategate scandal from football, from the Patriots? Anybody remember this? I don't know how. I don't remember when that was now. That was probably 10 years ago. One of the funny things, if you track like a pressure change in a football or something, you have to take the total pressure. And so a lot of people were doing calculations on like a football should be filled with like 8 psi. Well, a football, it doesn't have a fraction of an atmosphere in it. It has atmospheric pressure plus the 8 psi. So if you go back to the Deflategate scandal, there's actually some interesting conversions of pressure relating to psi, and that if you have like a tire with 30 psi in it, it really has 30 plus 14.7 psi in it. some interesting conversions from pressure if you go back to that scandal. Okay, so how do we measure pressure of gases? It's actually kind of funny. Like, use a digital gauge these days usually. You usually don't use an old-fashioned mercury-filled device anymore to measure pressures of gases. But the classic way, or the original way to measure the pressure of a gas was to use something called a manometer, which was kind of like a barometer, but it was specifically designed to be connected to a gas sample instead of an open dish connected to or open to the atmosphere. And so here what you might have is you would start with the mercury height equal with your valve closed to your gas sample. So the way you would start is you would take a gas sample, you'd connect it to a manometer, you'd have a valve here that would be closed, so you'd have this cylinder here that would just be at atmospheric pressure, because you just would have connected the device so it would have been atmospheric pressure, and then you'd have your mercury height equal, again, because you have atmospheric pressure here, you have atmospheric pressure pressing down here, so the heights would start off equal. Then you have a gas sample here and a valve that you could open. Then you open the valve, and then one of three things could happen. If you open the valve and the gas sample was already at atmospheric pressure, then the height would stay where it is. It wouldn't change at all. So another circumstance could be that the pressure of the gas that you have is above atmospheric pressure. So if the pressure of the gas is, let's say, greater than atmospheric pressure, what do you think happens? If the gas sample is above atmospheric pressure, it's going to press this mercury height downward. This height's going to respond by going upward. And we're going to end with a figure that looks like the one in the middle. And so what we could then do is we can track the difference in the height. So we can look at the height difference of the mercury and relate that height difference to the pressure of our gas. So the pressure of our gas would be atmospheric pressure, so we'd have to have like a barometer or some way of knowing atmospheric pressure at the time of the measurement. And then we would add that height differential. We would say, whatever the height difference is in millimeters of mercury, we're going to add to our atmospheric pressure. So the way you might do this would be to take the atmospheric pressure in millimeters of mercury and then track the height in millimeters of mercury, because you're measuring both in that same unit of millimeters of mercury. In theory, you could do them both in centimeters of mercury, where there's 76 centimeters of mercury in 1 ATM. So you could convert to other units other than millimeters, but millimeters would be the common way to do these problems. And then the other possibility would be that the gas sample is less than atmospheric pressure. So if we open our valve and the gas pressure is below atmospheric pressure, then the height of the mercury is going to move upward. So we're going to see the height here go upward, resulting in figure 3 here. And so we're going to see this is what it looks like when our gas sample has a pressure lower than atmospheric pressure. And then what we're going to do here is either one of two things. We're going to take our height as being negative. So our pH here would be, the height difference would be negative. Or we'll take the pressure of our gas as our atmospheric pressure and then minus the height difference. And we have to subtract to get a pressure that's below atmospheric pressure. And so again, we're going to track both of these in millimeters of mercury, or some unit that's common to both the atmospheric pressure and that height difference. This isn't the most common of problems, but it's like one where I like to talk about how you can use a device that looks like a barometer, we call it a manometer, to measure pressure differences. And then you can also then just imagine you start with the sample here at atmospheric pressure, you open a valve, and then you see pressurized versus depressurized, and how it changes the height difference in the column. Okay, so like I said, it's not a super common problem. You might see one in the homework, but it's not something you tend to see on exams on actually working out a pressure from a manometer. And it's also, in my opinion, if you need a pressure of a gas sample, you buy a gauge to do it anyway. So it's rare that you would actually use such a device. Although it is kind of funny, in grad school I often did use a device that looked like a manometer to measure gas pressures, but I think that was not all that common. So if you want to know a gas pressure these days, you just commonly use a pressure gauge. Okay, so what are some relationships between our variables like pressure, volume, temperature, moles? And so if you look at the relationship between pressure and volume, Boyles is somebody who studied and found that there's an inverse relationship to volume and pressure. So this might be better thought if you imagine a piston where you can press down on this piston here, and if you press down, we're reducing the volume of our gas sample. So if you lower the volume, you increase the pressure. So if you press down on your piston, you're increasing the pressure. So as you decrease the volume, you can think about how the pressure responds by increasing. So with decreasing volume, we increase the pressure. So we have an inverse relationship here between volume and pressure. And so then if you think about the way volume and temperature relate to each other, so again, imagine you have a piston here that's movable. So you have a movable piston, you have a gas here, and we're going to maybe put this in a water bath where we can heat the water bath up. So imagine you have a gas sample submerged in water with a movable piston, and I start heating up the water bath. What do you think happens to the gas sample? Starts absorbing the heat. Then what does that do to the gas particles, do you think? Probably makes them move around faster, and that's going to serve to try to increase the pressure, but we have a movable piston. So what's going to happen is that piston is going to move upward so that we can maintain a constant pressure inside of our cell. So the piston moves upward as the sample's absorbing temperature. So as temperature goes up, the volume of our gas goes up. You can also think about having like a balloon. If you warm a balloon up, you can expand it. If you cool a balloon, it contracts because the balloon's generally maintaining a relatively constant pressure. And so when we're looking at volume and temperature, we're imagining here that the quantity of gas isn't changing, the pressure of the gas isn't changing, but that as volume and temperature are related to each other, Charles found that there's a direct relationship. If you warm a gas sample up, it's going to occupy a larger volume. So we get a direct relationship here. And then we get, for volume and pressure, this is an indirect, or an inverse relationship. And so we can relate, if we imagine having pressure is inversely related to volume, then what you can relate is that our pressure times volume would be equal to some sort of constant value because we have constant quantity, constant temperature. We have that ideal gas constant that we're kind of not yet quite tying into the problem. But all this is equal to some sort of a constant. And so then what you can write is that P1V1 would be equal to P2V2. Now, how can we write this, or how do we know this to be true? Well, it's saying that if you have some initial pressure volume set of conditions and then some final pressure volume conditions, that they're both equal to the same constant. So if they're both equal to the same set of constants, they're therefore equal to each other. And we can do this with like volume and temperature too and see how it relates when we have the direct relationship. So we had the direct relationship here. So this will relate volume over temperature being equal to a constant. And then if you imagine having some initial volume, initial temperature, and you change those two values, but you don't change the quantity, you don't change the pressure, so the constant stays the same, then we're going to have V2 over T2 equal to the same constant. Therefore, V1 over T1 equals V2 over T2. Now, we can get these relationships here from Charles' law and then this one from Boyle's law. What we're going to see later, once we get back to the ideal gas law, we're going to kind of take a look at these gas laws that were studied individually, put them together, get back to the ideal gas law, and then we can look at the ideal gas law and get back to these equations too. So we'll look back at these equations and see how we can get to them once we get back to the ideal gas law in a few slides from now. And so this problem here is saying you have 2 liters of gas initially at 2 atmospheres. What pressure would the sample have if the volume of the gas is reduced to 1 liter? Okay, so we're looking at pressure and volume, so we're looking at a P1V1 equals P2V2 problem. So we have our P1 would be 2 atmosphere, V1 would be 2 liters, and then what would P2 be if V2, if the volume changes to 1 liter? So perhaps we have 2.00 atm at 2 liters. We have a piston perhaps that we're going to press downward upon, and we're going to change that volume and cut it in half to 1 liter. So what do you think happens to the pressure? Does it go up or does it go down? It goes up. So the pressure here should be going up. And so we set up our P2 which would be equal to P1 V1 over V2. And so this will be 2 ATM times 2 liters, and then divide by our V2, 1 liter, volume cancels, we end up with 4 ATM. So the pressure goes up. So now if we had miscalculated, like let's imagine we had an incorrect equation. Imagine you had P1 over V1 equals P2 over V2. We could have caught the mistake because we would have gotten the pressure would have decreased instead of increased. So if you're thinking of what should happen to the pressure here, you can easily calculate and catch mistakes. So our pressure here should end up at 4 atmospheres. Now this problem here, we have 2 liters of gas, such as in a container with a movable piston. So 2 liters at constant pressure at 25 degrees C is, well, I guess it would be cooled to minus 25.0 degrees C. What is the volume of the gas sample at minus 25.0 degrees C? Well, remember how I said you have to convert to Kelvin. So if we look at our equation and go V1 over T1 equals V2 over T2, and we're kind of, realizing V1 is 2 liters, T1 is 25 degrees C, that we can't just plug in negative 25.0 degrees C here. Volume doesn't flip to negative, right? And so this is where we have to go to that absolute temperature scale. So the reason why Kelvin works is 0 Kelvin is the lowest attainable pressure, and so that would be minus 273.15 degrees C. So not being able to go below minus 273.15 degrees C, add 273.15 to that, that's 0. So 0 Kelvin is our lowest possible temperature. And so we just have to convert these to Kelvin. We saw it earlier, which we probably, and we'll use this a lot. 25 degrees C is 298 Kelvin. Just add 273.15. I can't do simple math in my head. That's 248.15. And let's add our 298.15 over to this value here. Of course, those are only good to 4 sig figs, again, appeasing the sig fig overlords. And so if we solve for V2, it will be V1 times T1, or excuse me, it'll be V1 T2 over T1. Just doing our arithmetic. And then we can plug in our V1, 2 liters, times 248.15 Kelvin, and then divide by 298.15 Kelvin. And again, if we think what should happen, we have warm gas, cooling it, the volume should drop. We have that direct relationship. So if we drop temperature, we should drop volume, and it does decrease to 1.66 liters. But the key here is going to Kelvin and knowing that you have to go to Kelvin. So a lot of times in this chapter, you'll be given temperatures in degrees C, and in nearly every case, I can't think of any problem that can be solved in chapter 10 with the temperature still in degrees C. So we just have to know we're converting to Kelvin because we have to go to an absolute temperature scale. We can't use a temperature scale that can go negative and get correct answers in this chapter. So Avogadro studied the volume and quantity relationship. And this is really where you get the concept of gases don't have much of a dependence on the nature of the gas other than how many moles there are for the gas sample. And so volume versus number of moles, what was found if you had 22.4 liters roughly of helium, 22.4 liters of nitrogen versus methane, that would be comprised of an atmosphere of those gases where you had a mole of the gas. So if you took a mole of each of these gases, so a mole of helium is about 4 grams, a mole of N2, nitrogen's 2 times 14, so about 28.0 grams, and about CH4, 12 plus 4 times 1 is about 16.0 grams, that these all correspond to 1 mole. So if you take a mole of helium, a mole of nitrogen, a mole of CH4, you would have an equal number of particles inside of each of those containers. So you'd have the same number of particles of helium as there are N2 as there are CH4. And even though CH4 has 5 times the number of atoms as helium, it behaves the same. It has the same at the same temperature, it has the same pressure and volume. So the volume of a gas is independent of the nature of the gas other than the number of moles that are present. So the only quantity that really matters here is how many moles are there for these gases. So the same number of moles of any gas at the same pressure occupies the same volume. And so what was also found was that if you just added more gas to the container, like if you imagine having an expandable balloon, then the balloon would keep expanding. So you could have a larger volume if you just add more gas. So if you add to the number of particles, then you add to the volume. So volume became directly proportional to quantity. This should make sense. If you have no moles, you have no volume. If you have some moles, you have some volume. So if you keep adding to the quantity, we add to the volume. So we get a direct relationship between volume and number of moles, and then specifically the number of moles determining that volume, and not the mass. It's the number of moles that's important to describe a gas sample. So if we put together Boyle's law, which was the indirect relationship between volume and pressure, Charles' law, which is the direct relationship. Sometimes I get questions, you need to know the names. I don't think we use the names too often in terms of Boyle's versus Charles, and usually every semester it's something I have to make sure I remember which one's which. So I don't think the names here are super important. But what's important is the indirect relationship versus the direct relationships that we get here, and that when we put all this together, that volume is directly proportional to N and T and inversely proportional to pressure. And then if you imagine doing the P times V and then dividing by N times T, that this should equal a constant. And then that constant is what we call the ideal gas constant. And so this is just rearranging from this equation here over to one side, and then you can rearrange back to the Pivnert equation that probably is the form we've seen the most, where we have PV times nRT relating the pressure, volume, quantity, temperature to the ideal gas constant. And so if we now take a step back and go back to maybe like Boyle's law, if you remember, we had written P1 V1 equals a constant. Well, this is the constant. If we're at constant, if we're changing pressure and volume, if we're at constant N and T, so if we go to Boyle's law, for example, Boyle's law has constant N, constant T, and because those are a constant, then that's why pressure times volume is equal to an entire set of constants. And the constant we could see now is nRT, but nRT would just be a constant because N isn't changing in Boyle's law, T isn't changing in Boyle's law, and so then that's how we can have P1 V1 equals a constant, P2 V2 equals the same constant, therefore P1 V1 equals P2 V2. And then we can make this relationship even with 3 variables. Like if you imagine you have a container that can somehow change volume and change pressure. This might be like a balloon of some sort, maybe a tire. Tires can increase volume a little bit while they also can change pressure, and temperature can be changed within them as well. So if you're imagining maybe like a tire perhaps, or just, it doesn't even matter if you imagine what the device is, but if you're just saying, what does it look like to have constant N, where the moles of gas are more or less constant. Once you fill a tire, it doesn't have a leak. Once it's filled, the moles are constant. So here we could be writing that P times V over T would equal N times R. If N's a constant, R is a constant, then the only variables that can change are these 3 here. Then you have P1 V1 over T1 equal a constant, and then that would equal P2 V2 over T2. So we could write P1 V1 over T1 equals P2 V2 over T2 if we're at constant n. Yeah, so we can write relationships between 2 or 3 of the variables, or even all 4 of the variables. Like you could write, if all 4 of the variables are changing, then you just have PV over NT is equal to R. And if you change all 4 of the variables, they should still be equal to R. So if you have P1 V1 over N1 T1 equal to R, you change all these variables for the gas sample, they equal R as well. So P1 V1 over N1 T1 equals P2 V2 over N2 T2. So then we could write P1 V1 over N1 T1 equals P2 V2 over N2 T2. Then one last thing we can consider or just imagine with this equation would be, well, now go back to the idea that 1 or 2 of the variables are constant. So like if we imagine, like say volume and temperature are constant. So what if V and T are constant? So if V and T are constants means that they can't change. And so this makes V1 equal to V2, and then they cancel out, right? So like if V1 equals V2, then that cancels. And then the same thing here. So the terms that are constant cancel out in the equation. So if you go from P1 V1 over N1 T1 equals P2 V2 over N2 T2, and you just then say what variables are constant and can't change, they cancel out. And then we could write P1 over N1 equals P2 over N2. So we can write a variety of equations and relate a variety of variables to our ideal gas law. And we were kind of doing that with the V1 over T1 equals V2 over T2. So we can get back to that expression from what we were just looking at too. So if we go back, okay, it's not letting me go back. But if we imagine like making V and T the non-constants and like P and N the constants, and we get back to the same equation we had from Charles' law a couple slides ago. Okay, so our ideal gas law equation, PV is equal to nRT. Probably the next thing we'd want to do is try to determine what R is equal to. And so let's look at R here and try to say, well, how can we find R? Well, if we go back to the Avogadro's law kind of information that we had from Avogadro's law, we were looking at the pressure at 1 atmosphere of pressure, at some temperature, 1 mole of those gases had a certain volume. So you can kind of say if all gases at some temperature, pressure, and quantity have some volume, we can just plug that in here. So the gas constant is determined by taking 1 mole of an ideal gas and the volume it occupies at STP. STP is a weird thing. STP is standard temperature and pressure, where standard temperature is 0 degrees C. So standard temperature is 273.15 Kelvin and 1 ATM. So I don't think this comes up too much, but STP is 0 degrees C and which is 273.15 Kelvin. And 1.00 ATM. And so we can work the ideal gas constant out by setting R equal to PV over NT, so to solve for R, PV over NT. And then take that 1 atmosphere times the volume, 22.414 liters, and then divide by the moles and divide by the temperature in Kelvin. And if we look at these values here, we get the units that, if you've ever used the ideal gas law, you might have seen these units here. So in the units of liter atmospheres per mole Kelvin, it's 0.08206 liter atmospheres per mole Kelvin. So these are probably the most used units of R that we use in the class. And then there's another unit here that we use a fair bit, 8.314. We see it on here twice. The joules per mole Kelvin is probably the more used unit. We'll rederive R when we need this unit later. So we're not going to use that unit for probably until 1 or 2 lectures from now. So probably next Monday we'll rederive it, maybe on Friday. But we'll rederive R when we need the constants in a different unit, so we can talk about why we're rederiving it, why we need the other units, and what those relate to. But the one thing you can look at right away, if you look at the 8.314 number, do you see how those are SI units? So right off the bat, you can see that these are SI units. Because we see things like the joule, meters, Pascal, we're seeing the underlying SI units. So the SI unit version of R is 8.314. The liter atmosphere per mole Kelvin, this is like a non-SI unit of R. And that's mainly because we often, like I said earlier, we rarely actually use Pascal to measure pressures of gases. We're really more commonly using ATM or torr. So we'll use the liter atmosphere per mole Kelvin value more often. I believe it's on exams, so on the final info packet we'll certainly give you the ideal gas constant, but we're going to memorize that by doing problems. There's another unit, if we rederive the pressure but put this, because 1 atmosphere is 760 torr, so we could do 760 times 22.414 divided by mole and Kelvin there, and we would get 62.36 liter torr per mole Kelvin. But we rarely actually use this. This usually isn't a given on test. So if we give you a pressure of a gas in torr, we want you to calculate something related to the ideal gas law, you're just converting it to ATM and then using this unit here. So we're just going to usually change the pressure to fall into the units of R for the liter atmosphere per mole Kelvin value. Okay, so now what we can do with the ideal gas law is we can relate densities to the ideal gas law. So a density is a mass per unit volume. We can recall that moles are calculated by mass over molar mass. So we can do a little rearranging of the ideal gas law. So if we have PV equal to nRT, we could rewrite this as M over molar mass times RT, because that would be moles. And then we can, so that's a way you can see if you knew the pressure and the volume of a gas, and you knew the temperature, and you knew the quantity of gas in grams, we can solve and determine a molar mass. So we'll see some problems next time that relate to calculating molar masses from knowing things like pressure, volume, temperature, quantity of a gas. So there's ways you can measure molar masses of a gas sample by understanding or knowing some of the variables for our gas. And then we can also relate the density. So if we do some rearranging, so we can have pressure times molar mass equal to M over V times RT. So I've just divided both sides by volume and then multiplied both sides by molar mass. And then I can divide by RT and then end up with my density as M over V. And that's equal to pressure times molar mass over RT. So we can relate densities of gases to their pressure and the temperature of the gas and the molar mass and the nature of the actual grams per mole of the gas. So we can calculate densities for gas samples too. Let me advance to the next slide here. So the next problem we'll look at are calculating the pressure of certain quantities of gas in a certain type vessel at a temperature. And then we'll also then try to calculate the density of that sample in units, grams per liter. So we'll start with this problem in class on Friday and move into other applications of the ideal gas law. All right, guys, that's all for today. Have a great day.